All right, this is the notes on 7.6, inverse trig functions. We've already discussed these before a little bit from the first unit. If you remember, that's when we introduced the sine to the -1 power, cosine to the -1, and tangent to the -1 buttons on your calculator. But we need to make sure we understand the relationship between sine and its inverse and cosine and its inverse and tangent and its inverse. So to do that, I always like to start off with an algebraic example, and I'm going to write this up here. From algebra class, we learned about inverses, and if we had y equals 3x plus 1, the inverse of that would be thinking about solving that the other way. So we would say y equals, and this is the inverse, not the original y. And here they multiplied by 3 and added 1. So to our x, we would subtract 1 and then divide the whole thing by 3. So I want to prove to you that these are inverses of each other. If you take a number for x, say we want to plug in 2. If we plug that in, 3 times 2 is 6, plus 1 is 7. Notice that's our x and our y. An inverse takes the y value, plugs it into the input, and then shows that the output is also 2. It's the original input. So this would be 7 minus 1 divided by 3, and that is 6 divided by 3, which is 2. So this is the relationship between inverses. The input of the original function, which is this one, when we plug that in and get an output, the inverse function takes that output as its input and then gives us the original input from the original function as an output. So it's a backwards and forwards. So another way of thinking of it picture-wise is if you have a point here for your x, your original function takes you to the y, so this is f of x, but this inverse function takes you from this as the input back to the original as the output. Now, you're thinking, okay, that just seems like a way to say, how do I get backwards and forwards between the x and y value of an ordered pair? What we are going to be doing with trig functions is we have to remember the structure of what y equals sine x is. In this statement right here, x is an angle, and y is the ratio, not ration, ratio of the triangle. It's, remember, opposite over hype. Okay, so when we look at this, this is what a function is when it's a trig function. The input is an angle in radians or degrees, or a real number that we're considering, which is as a radian. And then when we work it out, we get a decimal or a fraction that is a ratio of the legs and the hypotenuse of the triangle, depending on which one you're doing. So when we write the inverse, so this would be y equals sine inverse of x, this flip-flops them. So now y over here is the angle, and the x here is the ratio of the triangle. So that's really what's going on. It's x and y are switching. Your domain and your range are switching. To be able to have a function having an inverse, you have to have a function that is 1-to-1. 1-to-1 means each x is unique and so is each y. The problem with the trig ratios is that, remember, they're waves. So you're going to get a lot of your y's are going to repeat over and over again. I mean, we have height of 1 and -1 multiple times as you go along the wave. So what we have to do is we have to limit what domain we say our inverses exist on. So we're going to talk about that in just a second. But I'm kind of trying to set the stage of what we're going to be doing with these problems today. And we're looking at how do inverse trig functions really work. So, things to know about inverse relationships. Y equals the inverse of x if and only if x is f of y. And remember that the domain of the inverse was the range of the original function. The range of the inverse was the domain of the original function. That's steps 2 and 3 here. If you compose the inverses together, so f and its inverse or inverse and f, you actually just get the argument inside here. It's the x or the y. Now the problem with that is, for this to be true, you have to be in your domain. So if you have the inverse inside, The answer is only x if the x inside here is in the domain of that inverse. And again, here, the y value can only be reported once you do the inverse and the original together if the y is in the domain of the function. So this is our problem here, is that we have to make sure when we say, because composition, if you compose something and they're inverses of each other, you've really just gotten the answer you started with. If I say here's a 3, here's a 7, if you do the function and then you do the inverse right after it, you go back to the original. So it's a circular logic here. And then the point AB is on the graph of F if and only if BA is on the graph of the inverse. We won't be doing a lot with that. And F inverse and F are reflections of each other through the line y equals x. Now these last two facts are much more useful if you're talking about inverses in 136. So we're not going to do a lot with that specifically. The inverse sine function, so we're going to talk about it first. So it's denoted as sine to the -1. It's not really a power, but that's what it looks like. So y equals sine inverse of x if and only if x equals sine y. So notice there's that switching of the variable here to show that that is just the switching of what's an angle and what's the actual ratio. Now here are our domains that we have to worry about. So for the inverse function, the inside number you plug inside there, so this x, so when I say y equals sine inverse of x, because this is now a ratio and this is an angle, remember sine fluctuates between -1 and 1 with its ratios. That's the height, remember, from the original function. And that means that the angle we pick, since it has to be something that we can define the signs on uniquely, is -π/2 to π/2. Now, let me explain why that is the way it is. If you think about our all science teachers are crazy, that gives us quads 1 and 4 that we're saying we use for our inverse. So we use quads 1 and 4 when talking about the inverse function. Now there's a reason for that, because this gives me positive signs and down here gives me negative signs. We don't want these two regions because they just repeat positive signs and negative signs. We want a unique value. So since we want a unique value, we have to stay in these two quadrants. So all the angles that we report when we talk about inverses, they have to be in those two quadrants when we're saying just find the inverse part of it. Now, if they want all solutions, we would then say, okay, it's in the inverse, and then we'll use that to find the match in the other comparted area. So like if I do want all positive sine, where sine is 1/2, then that's when we would give both parts. But if we're using the inverse and we want a unique answer, we should only give the one that's there. Now, this is just rewriting that. So the domain of the inverse sine function is -1 to 1, and its range is -π/2 to π/2. The notation y equals sine inverse x is read y is the inverse sine of x. The equation x equals sine y in the definition allows us to regard y as an angle. So y equals sine -1x, or inverse of x, can also be read as y is the angle whose sine is x. And remember that y has to be in our domain. The inverse sine function is also called arcsine. So you can write arcsine of x, and that is equivalent to sine inverse of x. They are, I would say, interchangeable. So there is all we need for the sine. So let's look at some examples. So notice this time, instead of having an angle inside, because it's an inverse, we have a ratio inside. This says what angle has a sine of 1/2, because we're asking for the inverse here. So sine y equals 1/2. So see, we rewrite that by switching those and changing back to the original function. And the answer between -π/2 and π/2 is π/6 if you think about your unit circle. If we want the negative version, notice we get -π/6. We want to stay in quads 1 and 4. So everything that they report in this chart is all for values that are between -π/2 and π/2. And this is what the final step of this says. It is essential to choose the value y in the range -π/2 to π/2 of sine inverse. Thus, even though sine of 5π/6 is 1/2, the number y equals 5π/6 is not the inverse function value sine inverse of 1/2. So you just have to be aware that that is now unique. We're saying if you take sine inverse of 1/2, the answer you're supposed to report has to be in this range. Okay, here's some properties real quick that we're going to use. If you have the sine and its inverse back to back, in other words, you're composing it inside of the other one, so this is called composition, the answer is typically just the variable as long as a condition is met. If the inverse is inside here, then this has to be between -1 to 1. Otherwise, we can't say that it's just the number. If you have the regular sign inside, then to be able to do this where we say that it's just the number y, this has to be between -π/2 to π/2. So remember, if sine is inside, you're dealing with an angle. If sine inverse is inside, you're dealing with the ratio. So let's just look at one real quick. Notice this is the first case, sine inverse of 1/2. This says find an angle that's inverse, that has a sine ratio of 1/2. And it had to be in, remember, our correct quadrants for inverse. Then you would plug that into sine of the angle and you get the 1/2 back as long as this is in the correct domain. So since the inverse is inside, as long as the number inside is between -1 and 1, a sine and its inverse just gives us the number. So this meets the condition between -1 and 1. So there's nothing to work out on those if they meet the correct condition. Now we will see one in a minute that doesn't meet the correct condition. This time the sine, regular sine, is inside and the inverse is on the outside. So if the regular sine is inside, you should be looking at an angle here. As long as this angle is between -π/2 to π/2, which is our domain for our inverse sine, then we're good, and it is. So the answer is the composition and the function cancel each other out since they're opposite operations, and we just get π/4. So C is a little bit different. C has sine inverse of sine of 2π/3. This is not between -π/2 to π/2. So we have to actually do this a little differently. That doesn't mean we can't solve it. It's just not going to be the number is the answer. Okay? So you come over here and you draw a little picture and you think about where 2π/3 is, which is over here. And 2π/3 is a 60-degree reference angle. So remember, that means this is 30. So this is square root of 3/2. This is -1/2 since x's are negative in this quadrant, and this would be 1. So sine of 2π/3 is, remember, opposite over height. So sine of 2π/3 is square root of 3/2. Where do we have a sine value of square root of 3/2 that falls within the -π/2 to π/2? So that's really what we're going to be looking for. So if this doesn't fall in the correct region, we think about what that triangle looks like, what quadrant it's in, and we find the matching sine value that either would be in quad 1 or quad 2. For sine to be positive, we have to be in quad 1 because sine is, remember, the y value. So this would be a 60-degree angle, or another way of thinking of that, since we're in radians, is just π/3. So this one would be π/3 because that would put us in the correct quadrant for the inverse functions, which, remember, quadrant for inverse functions has to be 1 or 4. So that's how this works. If the condition is met, it's really easy. An inverse and its original function just really are opposites of each other. So as long as you're in the right domain, you just get the answer. If you're in the right angle for when the inside part is the original, you just get the angle. If you have the wrong angle, you draw it out and you think, where would the right angle be for this situation, which has to be in quad 1 or 4. So it had to be in quad 1 since that's when y is a positive value, since sine is y. Okay, so that's the end of the inverse sine. We're going to talk about the inverse cosine next. All right, so the other trig functions can be used to introduce the inverse trig functions. So the first thing, and they didn't show you this on the sine part in the book, but how they determine the interval that we're going to use for our inverse is they actually look at the wave and they pick a region of x values so that they get every possible height of this wave. So if you start at 0 and you go to pi, you've gone from the highest to the lowest point of that cosine wave. So that's how they determined that cosine should be 0 to pi. Whereas sine, they use negative pi over 2 to pi over 2, because in that case, remember, sine actually has a crossing point there, so it goes from its highest to its lowest. So the reason these are different is because sine and cosine are just adjusted a little bit off of each other. They really are the same shape, they're just one starts at a different position. So that's why I wanted to show you this, is that's how cosine is different. So cosine still has the x has to be, the ratio for the triangle has to be -1 to 1. Remember, that's because we're on the unit circle. And then the cosine's angle, though, the y value, the answer, has to be between 0 and pi. So same situation here. It's essential we choose y values in the 0 to pi range. So again, cosine and cosine inverse would cancel out each other if we have the x here, this is the inverse being inside, being between -1 and 1. If the original function's inside, you need it to match the angle description. So remember, when you have original function, the inside value is an angle. When you have the inverse function, the inside value is the ratio of the triangle. So for these to cancel out, this has to be between 0 and pi. And there's another chart here just showing you that they've picked now, when they look at these cosine inverse problems, they're picking angles that are between 0 and pi. All right, so look at this one. Let's look at A. This is cosine and cosine inverse. If the inverse is inside, you're talking about a ratio inside here. Remember, that's your input. So as long as this is between -1 to 1, we're good, and it is. So if you have the cosine and its inverse, they really do just cancel each other out, and we get the -0.5. For this one, this is now the angle part is inside, cosine of a theta. So since this is checking between 0 to pi, now pi is actually bigger than 3.14, so we're good here because that's just the approximation for pi. So this would just be 3.14. So as long as they meet the conditions we've set out for what is acceptable as your argument of the inside of that function, anytime you have the original function and the inverse back to back or composed, then the answer inside would just be the x or y value that's inside. When we get down to C here, notice they're not even the right trig functions. This is a cosine inverse and a sine inside. So we need to take this and draw a picture to see what's really going on, because we don't even have the right trig ratio, relationship right here. This is inverse of cosine and regular sine. Okay, so if we're at -pi/6, that would be going down, and it would be a 30-degree angle. And this is 60 degrees. So this would be -1/2. This is square root of 3/2, and this is 1. Now, we had sine of -pi/6. So what would that be according to our picture? Well, that would be opposite over hype, so this is -1/2. So now we can take this actual value and replace this whole statement with that -1/2. So then this says, what's cosine inverse of -1/2? Now, just to let you know, you could attack all of these problems this way. You could draw a picture for the inside and then work your way back to the outside. But if the properties were there, it's a lot quicker just to say it's the answer. Now for this, we're dealing with the inverse function. So we're asking the question, what angle between 0 to pi has a cosine value, if this will write, sorry, cosine theta value of -1/2. So we're thinking about this now in terms of what angle does that. So remember, all science teachers are crazy, and we have to be in quads 1 or 2 when we're dealing with cosine inverse. Now over here, cosine is going to be positive, so it has to be in this quad. And for cosine to be 1/2, you have to think about this for a second. That means that the adjacent angle has to be the 1/2, or the adjacent side, sorry. So that's -1/2. This is square root of 3/2. So that means that's a 60-degree angle right there, okay? So this would make this 2 pi over 3. So the answer to this one is 2 pi over 3. So that's the answer. So if they don't match, or if it doesn't make sense to try to do what we did with the rule, you can always draw what the first picture represents, find the answer to that, replace it into the outside function, and then find the answer for that part. Just remember, anytime you're dealing with the inverse, you have to make sure you're dealing in the correct quadrants. Okay, and then the last one is the inverse tangent function. This one is also defined on negative pi over 2 to pi over 2, so quadrant 1 and 4. But this time, tangent can have any number we want for x, because if you remember what the tangent function looks like, you get a bunch of these. So there's no highest and lowest, because remember, in a sine wave or a cosine wave, we never go above or below our highest and lowest point. This is any y value goes. And if you actually draw the inverse tangent, we're not going to make you draw it, but if you see the graph of inverse tan, notice that it flips that on its side. So that tells us right there that any x is okay, because I can go anywhere on the x-axis and find a blue graph. I do have asymptotes, but they're on the horizontal now instead of the vertical. Because remember, tangent of x had vertical asymptotes. So the inverse has horizontal asymptotes. So essentially the same rules apply, but the nice thing is the tan with the inverse inside, so tan composed with tan inverse, it will always just be the answer inside, because there's no domain restriction for that inverse function part for the x. The angle part, though, does have to follow either quad 1 or 4. So, but there is a difference here. Notice, remember, in sine, you could have equal to. In tangent, those are not equal to. Tan inverse of tan of pi over 2 is undefined. Okay, we can't do that part because we can't be equal to that. So just be aware, and that's because of those asymptotes that we talked about just then. So we can't do that part. All right, so let's find the exact value. So this one has the inverse inside, so as long as this x is a real number, it's the answer. So it's just going to be 1,000. So any real number, yes. For this, when you have the original tan inside, your angle has to be between negative pi over 2 to pi over 2, but remember, not equal to either one of those. And pi over 4 is in quad 1, so this one is just going to be pi over 4. Okay, so let's talk about this one. Now, they were using the inverse differently. Remember, this means tan inverse of tan pi. They just wrote the arctan there. So tan pi is not between negative pi over 2 to pi over 2. So we need to think about what is tangent of pi. So come over here, and this is tan of pi. And if we're on the unit circle, that would be the ordered pair negative 1 comma 0. Tan is always y over x, which is 0 over negative 1, so that's just 0. And then we think, okay, so this part says now, because that's 0, this is going to say arctan of 0, because we're replacing the tan pi with the 0 answer. So this part is asking us what angle has a tan theta ratio of 0. Sorry, my computer's a little slow. In negative pi over 2 to pi over 2. Okay, so in our correct quadrants. So if we think about over here, because we're dealing with the inverse function, when would tangent have a ratio of 0? And it's going to be this mirror point right here. It's going to be when we have 1, 0, because this is also, so tan of 0 is 0 over 1 as well. Now, it doesn't matter that the other one was negative. It's just, does the ratio come out to the same? And it is a 0. So this would actually be an answer of 0. Now, I want to distinguish something for you. The 0 that's in here is a ratio. The 0 answer we're giving is the angle. So just be aware of that. So that's not that they match, it's this is the ratio here, and this is the angle that coordinates with that. Okay, so we did the sine inverse, the cosine inverse, and the tangent inverse. Now we're going to use this to solve some equations. All right, so look at the directions for this one. It says use inverse trig functions to solve the following equation between 0 and 2 pi. So we are going to be finding more solutions than the actual inverse will let us find, but we're going to do something similar that we've already done before in the past. So we've used the inverse button from Unit 1 to find the ratio in the correct quadrant, and then we found the other answer, remember, from finding the place where that same ratio would appear. So I'll kind of show you what I mean in just a minute. The problem is this original equation right here, even though it's set equal to 0, it does not factor. So we want to try to factor this. Now, I don't prefer to factor it with the cosines in there, or excuse me, use quadratic formula. So I'm going to let all of my cosine x's become the letter u. So that would be u squared plus 4u minus 1. This is called a u substitution. So then I notice that my a term is a 1, my b term is a positive 4, and my c term is negative 1, since this does not factor. So we're going to use quadratic formula. So u equals negative b plus or minus square root b squared minus 4ac all over 2a. So that's the quadratic formula, which is usually an x, but in our case we're using the letter u. So just kind of write that formula up here for you in case you don't remember it. It's a good one to have memorized. Okay, so if we work this out, this would be u equals negative 4 plus or minus the square root of 16. This is negative 4 times negative 1, so that'd be plus 4 all over 2. And then we would have negative 4 plus or minus the square root of 20 over 2. And we need to simplify that 20. Remember that it has a perfect square that goes into it. It's 4 times 5, so that would be 2 on the square root of 5 over 2. And every outside number is divisible by 2, so we can actually reduce this to negative 2 plus or minus the square root of 5. Now let's talk about what we just discovered. So remember, u is cosine x. So that really means that cosine x equals these two solutions. So let's write that down. So we take these two answers and we say, okay, cosine x either equals negative 2 plus the square root of 5, or cosine x equals negative 2 minus the square root of 5. Because we want to find out if there is an angle that makes sense for these, we would then do the inverse function. Now, before I actually do the inverse, I am going to check to make sure that these are between negative 1 and 1, because if they're not, you're not going to be able to take the inverse. So let's do square root of 5, and then take away 2. So this is about 0.236, so that is definitely between negative 1 and 1. And then it's negative, so it's square root of 5, negative, and then we have a minus 2 again. That is not going to be. So I'm going to show you what happens. This is not between negative 1 and 1. So if we try to do the inverse, you're going to notice that we can't work it out. Wait. Yes, that's correct. So the inverse is cosine inverse of negative 2 plus the square root of 5. That'll solve for that x. And I'm going to just show you that this doesn't work in case you forgot to check that. Okay, so let's do the first one. So negative 2 plus the square root of 5. And we need to make sure we're in radians because that's what it told us to be in the problem. It said 0 to 2 pi. So I've got that. So I'm going to do the inverse cosine. And that comes out to x is approximately 1.33. Okay. If we try to do this one, negative 2 plus, or actually it's minus this time, excuse me. Start over. So negative 2 minus 5 square root. So that was negative 4.236. If we try to do the inverse cosine of that, see, we get invalid. This is because this is not between -1 to 1. So we can't do that one. Okay, so now you think, oh, well, do I only have one solution? No. We need to find any place that this could be possible. So if you think about where is 1.33, so pi divided by 2, that's, remember, 90 degrees, is 1.57. So this is about 1.57. So 1.33 is somewhere over here. Okay, so that's my x right now. So what we're looking for is there another place where cosine is positive and has that has the same angle measure as this? So give me just 1 second. My computer's freezing up a little bit. So remember that we are looking at the angle is the 1.33 radians. So we want to find another place where cosine has a trig value that is positive and has this same reference angle measurement. So for cosine, that's going to be down in quad 4. Sorry, that's not quite symmetric. So this would be 2 pi minus the 1.33. Now, even though that's not in the typical cosine's inverse, the inverse gave us just this singular answer. And we did this, remember, in Unit 1, where we said that the other answer has to be where that trig value has the same ratio values. So if it's positive here, we need the other place where cosine is also positive. So 2 pi minus the 1.33 will give us the other value for our x, which is 4.95. So the two x values that work for this one are approximately 1.33 and 4.95. Now, if both versions had worked, so remember we had one that the cosine didn't make sense because this wasn't between -1 and 1. If they had both worked, we would have gotten 4 different answers, and that is what's going to happen in this next one. So we're using inverse trig functions to solve the following equations, 0 to 2 pi. This time we're doing sine, though, and I'm going to use another substitution. I'm going to let u equal sine of t so that we can factor this, or, well, I don't think this one factors either. No, we're going to have to use quadratic formula again. You can try factoring, but it's going to get you nowhere. So this is 5u squared plus 3u minus 1 equals 0. So a is 5, b is 3, c is -1. So u equals negative b plus or minus square root b squared minus 4ac all over 2a. So this would be -3 plus or minus the square root of 9, and that's going to be plus 20 all over 10. So u is -3 plus or minus the square root of 29 over 10, and 29 is not a perfect square or has no perfect squares that go into it. So now we can back substitute and change the u back to sine. So I have two different versions I'm going to try to solve. Sine t equals -3 plus the square root of 29 divided by 10, and sine t equals -3 minus the square root of 29 divided by 10. We need to check, since these are sine functions, we do need to check to make sure we're between -1 and 1 for both of these. So -3 plus the square root of 29, oops, so -3 plus 29 square root, hit enter, divide by 10. Notice I didn't clear anything. This one's about 0.24, just double checking it. And this one, minus 29 square root, hit enter, divided by 10, is -0.83 or 84. So both of them are between -1 and 1, so we can proceed with the inverse. So t will equal the inverse sine of this big fraction, and that'll be t1. We'll call that t1. And t2 will equal the inverse sine of that fraction, which I have no room to write. So I'm just going to put a little arrow. So let's work it out. So we have to still be in radians because it's 0 to 2 pi. So 3 is negative plus the square root of 29 divided by 10. We just want the whole decimal. And then we want to take the inverse sine of that, this time not cosine. And that is 0.02. I'm going to double check myself real quick on that one. Plus 29 square root divided by 10. And then we want to take the inverse sine of that. Yeah, I think it's the 0.24. I think I hit the button twice. All right. That must have been what happened last time because that seemed very small. So T1 is 0.24. Okay, let's do T2. So 3 is negative minus 29 as a square root this time. And then hit enter. Divided by, actually no, that did not divide. Sorry, when I use this calculator, I have to remember that it is not as cool as a scientific calculator. You have to enter things very carefully. So negative 3 minus 29 square root, hit enter, then divide that by 10, then take the inverse sine. So this one is negative 0.99. Okay. So remember, those are just the reference angles for these. So and that's, this one is a quad 1 because it's giving me a positive. This one's a quad 4 because remember, sine inverse goes in either quad 1 or quad 4 because it's a negative. So we're going to draw a picture for those. The 0.24, I'm going to do just this one by itself. So that's 0.24. Now notice that is when sine is positive. The other place where sine is also got a positive ratio is over here. So this would also have a reference angle of 0.24. So when we want to find out what this one is, we do pi minus that one. So pi minus 0.24 will give us the measurement from 0. There we go. So pi minus 0.24. Clear this out. Is 2.90. So 2.90. So that's an answer. So is 0.24, because that is measuring from 0. And then let's think about the other case, which was when we were in quad 4. So in quad 4, we got this negative 0.99. Now I know that that's not in a different quadrant because the inverse has to either be in quad 1 or quad 4. So we use the inverse button and it's negative, so it's down here. Now I want to know what that is between 0 and 2 pi. So I need to do 2 pi minus the 0.99 to actually get a radian measurement that's positive because they do want us to report our answer between 0 and 2 pi. So 2 times pi minus the 0.99 is 5.29. So this is actually 5.29 over here. Okay, now because sine is negative here, there's another place that sine is negative, and that is in quadrant 3. So we should have another matching 0.99 angle right here. And this one would be pi plus 0.99 because we're going past 180. So pi plus 0.99 is 4.13. So 4.13 is an answer right here. So notice, you get 4 answers, but they're very specific. There's one that you get, if both sides work, you usually get one in quad 1 for sine, and then you get a match over here in quad 2 that has the same reference angle. And then for the quad 4 answer, we get a match in quad 3 that has the same reference angle of 0.99. And that's because of the way the signs are. So in sine, your first quadrant always matches with your second quadrant one, and your fourth quadrant always matches with your third quadrant. That's different if you're doing cosine, because remember, cosine has different signs, and plus its inverse goes from 0 to pi. So this is how you find all four answers. So let me write those down. The T answers were, and from least to greatest, it would be 0.24, 2.90, 4.13, and 5.29, and I don't know why they just erased. So a little bit weird, but I will try to write them again. Okay, so that let me start over. Just had to reboot the PDF. The answers from order to least to greatest are 0.24, 2.90, 4.13, and 5.29. And remember, those are the radians of those angles. That's the radians as a real number. All right, so that was the last example in the notes, but there's one more I want to throw in. So I'm going to need to open up either a Word document or something else. Let me save this really quick. I usually have one on a daily worksheet that's different, but because we're so close to a test day and me not being there today, I'm not going to give you guys a daily worksheet to do. So let me save this real quick. But there is one other one that I always like to show in class, kind of when you do it in groups. So let me pull that up real quick. It's in the textbook. And it's this example right here. So let me pull up just a blank Word document to show you this one on. So we're looking at, so I can copy it, secant of arctan of 2/3. So secant of arctan of 2/3. Okay. So when you look at this, we're supposed to be evaluating this or working it out. This is, remember, tan inverse. A lot of people like to see it that way. So this is tan inverse of 2/3. Secant and tan inverse are not opposites of each other. They're not inverses of each other. So we have to take this information to somehow figure out how to find the secant. So when we think about it, that tangent is actually giving us some information about a triangle. Because when you see tan inverse of 2/3, imagine that being equal to the y, the angle. We can rewrite this as tan of y equals 2/3. So this is really just like an angle y, and these are the ratios of the side of the triangle. So 2 is going to be your opposite, and 3 is going to be your adjacent. So that means we're solving for the hypotenuse. Okay, if we can figure that out, then we can find secant of what they ask. So when we look at this, we're going to figure out this by Pythagorean theorem. This would be 2 squared plus 3 squared equals h squared. So this is 4 plus 9 equals h squared. So h is going to equal the square root of 13. Okay, now that means that what I'm looking for when I say I'm trying to find, okay, so here's the inverse. I don't even care what the angle is. What I'm trying to find is now, this is our angle. So we're trying to find secant of y. We use the tangent information to help us set up the triangle. So when we try to find the actual secant of y, you probably want to switch that to 1 over cosine of y, because that'll be easier to find from the actual triangle. So cosine, remember, is adjacent over hype. And then we don't like having a fraction inside of a fraction, so we'll multiply top and bottom by square root of 13. So we get square root of 13 over 3. So the inside part that they give you, if they have the inverse inside your composition, you can usually use that to find the sides of the triangle it's referencing and find the other side by Pythagorean theorem. Once you know that, the inside, you're done with that. You just want to find what is the secant of this new triangle with that same angle as your reference angle. So that's it. I just wanted to make sure I did one of those as well, since it's a little bit different. And I will see you guys on Tuesday. Hopefully you'll have lots of questions from the review packet for me. Have a good weekend.